driving along. And if our car is driving along and we have an odometer, we have some really old-fashioned car that only has 3 places, a Model T. And so we're going along, we've driven 1 mile. We increment the last spot. We've driven another mile. We increment the last spot again. We drive another mile. The last place increases by 1 again, and again. And we keep going until we hit 9. Now we've had a problem. Why? Because we're counting in base 10, otherwise known as decimal, which is a counting system where we only have 10 values, 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Once we hit this 9, we can't get any larger. So what do? You reset back to the lowest. That becomes a 1, and then you increment the next column. And I know we all know this, right? And so then as you went, it would start repeating that, right? And so on until you got to 0, 1, 9, and it's going to happen again, right? We've maxed this one out. We can't increase it anymore, so it gets reset back to its lowest value, and the next column gets added to 1. And we keep going, and we get to 0, 99. All right, that one can't hit anymore, so it gets dropped down to 0. We increment that one. Well, we can't. So that one drops down to 0, and we increment the next column by 1. And eventually you would get to 999, which is the largest value that 3 decimal places can hold. What's going to happen then? Well, you'll get rollover. You'll get overflow if you try to add 1 to that, right? Because really it should be 1,000, but we only have 3 places to hold it. They would all get reset back to 0. And we have a problem there. So that's overflow. Now I'm going to ignore that one for now. So when we're counting in base 10, in grade school we called that the ones column and the tens column and the hundreds column. What are they really? It's the 10 to the 0th power column. It's the 10 to the 1st power column. And it's the 10 to the 2nd power column. Right, so if you have the number 339 or 369, and we wanted to figure out what that was equal to, well, that's a 3, that's a 6, and that's a 9. So this is 3 times 10 to the power of 2 plus 6 times 10 to the power of 1 plus 9 times 10 to the power of 0. Now that to the power of bit becomes a little bit annoying. Any number to the power of 0 is 1. Doesn't matter whether it's 1 or 1 billion. 1 billion to the power of 0 is 1. So really this is just 9 times 1. And 10 to the power of 1 is 10. So really that's 6 times 10. And 10 to the power of 2 is 100. So this is 3 times 100. So we could say 3 times 100 plus 6 times 10 plus 9 times 1. And then if we added all that together, that would be 369. Now lo and behold, that's what we started with because we converted from base 10 to base 10. That's like converting English to English. Yeah, that's pretty easy, right? You just copy down the words. But the same concept is going to apply in just a little bit to something else. What if we have what's known as octal? Octal is a counting system that has only 8 digits rather than 10. So it counts up 0, 1, 2, 3, 4, 5, 6, 7, and then it ends there because that's 8 digits. So if we were driving our octal car, it would go like this: 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. We've maxed out our system already. Can't keep going. We can't go to 0, 8 because there are no 8s in octal. So we reset the last column to 0 and we add 1 to 1. Right, and we keep going, and eventually we would get to 7, 7, and then we would increment that one. Well, it's hit its max, so it reset to 0. Well, that means we have to increment that one. Well, it's hit its max too, and that's where overflow occurs, or it becomes 100 if we have 3 digits rather than 2, right? Like that. Okay. So The number 10 in octal is by no means equal to the number 10 in decimal. Why? Well, because if we were going to count them out decimal-like, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That was 9. So, what we would have to do in order to perform reliable conversions is to create a little chart where the first place is 8 to the power of 0. And the next place is 8 to the power of 1. And the next place is 8 to the power of 2. Dot 6 to the power of 2. 8. So if we were going to figure those out, that's a 64. 8 times 8 is 64. 8 times 1 is 8. And any number to the power of 0 is 1. So we have 3 columns here. We have the 1s column, the 8s column, and the 64s column. So if we have this number here, well, let's make up one again. If we have 3, 2, 9 in base 8 in octal, and we want to convert that to base 10, we would add them up like this. 3 times, well, what's the first places? What's the first column here worth?
8 to the power of 2.
Yep, so that's 64. I'm going to skip the power of 2. That was hard to type. So that's 64 plus, what's the next column? 8 to the power of 1, which is 8. So 2 times 8. And what's the last column?
9 times
Yep, 9 times 1. Okay, so honestly, I can't do that in my head. I don't know what 3 times 64 is, so forgive the little excursion up here. 3 times 64 is 192. Once you set it up like that, that's enough for me. I don't care about the math at this point. I'm going to paste this entire expression into Google and it'll tell me what it is. 217. Equals 217 in base 10. All right, octal really isn't used anymore. I'm not sure why it ever was, but computer engineers and computer scientists love things with powers of 2, being as all data is stored fundamentally in powers of 2, because we only have 2 digits, 0 and 1. So we hop into our binary car. Binary is base 2, which is only got 2 digits, 0 and 1. So we have our binary car with its binary odometer, and we drive a mile. That's cool. But we've already maxed it out. So we reset the last one to a 0, and the next one increments. Then we drive another mile. And then we drive another, well, that one's maxed out, so that one's going to become a 0. So we add 1 to 1. Whoops, that one's maxed out too. Right? Like that. And it's going to keep going like that. But it's not going to take very long to max out these values. All right, now we've done that. What's going to happen the next mile we drive? What does that turn into?
1, 1, 1, 1.
Not 1, 1, 1, 1. We would increase the last one, which would do what to it? Would drop it to 0. And so then what happens? We add 1 to that one, which drops that one to 0. So we have to add 1 to that one, which drops that one to 0, and we get 1 there. That makes sense? Okay, so now it would just repeat the same sequence that it did before. 1001, 1010, 1011, 1100, 1101, 1110, and 1111. And so if we were going to count these out, how many different possibilities do we have? Well, we've got, that's a 0 in base 10. Let me use tab in case I want to convert these to something more interesting later. That's a 1. I'm just going to count in base 10 now, so there's no tricks involved at all. Okay, so with 4 bits, if we treat these as unsigned, meaning you can't go negative, you have 16 different possibilities You can count from 0, 0, 0, 0, all the way up to 1, 1, 1, 1. We have 16 different possibilities, 15 of them, plus one more for 0. There's a formula which will tell you how many possibilities you have, which is if you have x bits, the number of, of possible values is 2 to the power of x. So in other words, if you have 4 bits, that's 2 to the power of 4, which is 16 different possibilities. 8 bits, I happen to have that one memorized. 2 to the power of 8 is 256. So like, I don't know if any of y'all ever played one of those old original Ataris from the 70s, playing Space Invaders or whatever, but they had incredibly primitive graphic chips. And the idea that it could display 16 colors on the screen at the same time is frankly optimistic. But that kind of implies that their graphics system was using something set up to where each color was represented by 4 bits, or less maybe. If you had a black and white system, you could just use 1 bit to control whether a pixel was on or off. Like a black and white Mac, or a Windows machine from 1979 or whenever Windows first came about. Anyways, 89, excuse me. So if 4 bits can hold a maximum of 16 values, 8 bits can hold a maximum of 256 values. If you had a Nintendo, you were really cool. You threw away your Atari. It had 8-bit chips in it. And so did your Apple II computer and your Atari 800 computer and stuff like that. They had 8-bit chips in them. So they could display, the graphics also, I believe, were 8-bit inside them to some extent. They could display one of 256 colors on the screen. So the pictures on your Nintendo could look a lot better than they did on your old Atari. Then you bought your Sega Genesis or your Super Nintendo. And that's 2 to the power of 16. And I would have to go and calculate that. I think it's 65536, but Google those all. So 2 to the power of 16 is 65536. Obviously, that's a bigger color palette, 65536. A lot more colors available. That's why games on your Genesis or on your Super Nintendo looked a heck of a lot better than on your plain old Nintendo. Or that's why when you upgraded your original IBM PC in 1989 and put a 8-bit video card in it, you actually got some colors, and then you put in a 16-bit video card and you got a lot more. So this is also known as 64K. Now if you've done any chemistry or physics classes, you think of K as meaning 1,000. And so in physical units, K means 1,000. But to computer scientists, K means something slightly different. It means 1024, which is a power of 2. 2 to the power of, I don't know, 6, 8, 10. Let's find out. 2 to the power of 10, 1024. Okay, so anyways, yeah, so that's 2 to the power of 10. That's just a kind of a little note. And then there's something known as a megabyte. You could roughly say that a K is about 1,000. That works close enough. I have 1 kilobyte. So 1 kilo in this numbering system in computer science is about 1,000. 1 mega is 1,000,000, 2 to the power of 20, which is about 1,000,000. And then giga, I have an 8 gigabytes of RAM in my new computer, is another number, about 1 billion. It's 2 to the power of 30, which is about 1 billion. And then you have a lot of pictures stored on your computer, so you buy a terabyte hard drive. A tera is 2 to the power of 40, which is about 1 trillion. The reason I mention these is because if I wanted to convert that number to find out how many K that is, I would have to divide it by 1024. We would find out that that is equal to 64K. They used to sell computers with only 64K kilobytes of RAM in them, like the Commodore 64. It has 64 right in its name. It could have 65,000 bytes in it. 65,000 numbers in its memory. That's really not very much. And the Nintendo had even less, but the cartridges you could load into them would have extra, kilobytes that they would store the programming on. So anyways, if something was limited to 64 kilobytes, that implies that its memory architecture was a 16-bit memory architecture, that the memory bus was 16 bits wide. And that was very true. And before that, they had 8-bit buses. And so they could access only 256 bytes. That sounds incredibly primitive. So I bet that 16 bits, was a standard. Certainly came about in the 70s. And, they had other computer architectures other than integrated circuits, which did things in a different way. But in effect, the memory circuits inside your Commodore 64 or your Nintendo or anything that was limited to 64K was a 16-bit system, meaning that it had 16 bits. Bits are zeros and ones. The bit is the smallest possible value. It's a 0 or a 1. And so if you have 16 bits, it could go all the way from, I'm going to type them out, but I'm going to put spaces between them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It could go all the way from that to that. That would be the largest value. And so this would equal 0, and this would be equal to 1 less than the maximum value that 16 bits can hold. So it would be 65535. Now recently, you've heard about the difference between 32-bit Windows software and 64-bit Windows software. And those number of bits refers to the architecture that the chip can address in memory. For a while, the Intel processors that were used in desktop computers and laptops had 32-bit addresses. I'm not going to type 32 bits outright, but I would just take that and I would double it. Well, what's the maximum value that you could store with 32 bits according to our equation? It would be 2 to the power of 32. Which equals, Google will tell me, 2 to the power of 32. Huge number, but it's not that huge. Why is that not that huge? That's only 4 gigabytes. Now I say only, right? Back in the 80s, 4 gigabytes was an insane amount of RAM, right? You'd buy a Cray supercomputer and it might not have 4 gigabytes of RAM installed on it. But, by the beginning of the 2000s and the 2010s, gigabytes were, yeah, I have 4 gigabytes in my computer. That's pretty cool. But that's an upper limit. And so say you like running Photoshop and Call of Duty and Mass Effect and all these other things on your computer at the same time. 4 gigabytes might not be enough. And so that's why the transition was made by the hardware manufacturers until, specifically to go from a 32-bit wide memory bus to a 64-bit wide memory bus. And so with 64 bits, the amount of RAM that you could address is absurd. 2 to the power of 64. I come up here and I type that in, 2 to the power of 64. That's a huge number. That's absurd. If I do that and I divide it by a trillion, 1e to the 12, that's like 18 million terabytes. Obviously, the 64-bit architecture supports so much RAM that we're not going to see limits of that amount of RAM for a little bit of time, right? The rule of thumb is supposedly that computing power increases by a factor of 2 every 1.5 years or something like that. That was called Moore's Law, and it worked remarkably well to plot speed and memory progress for a long time. But you got to the point where the limiting size of physics would limit how fast you could make a computer and how dense you could make your RAM. Because once your little memory traces got too small, then you get crossfeed between them. Or once you had a computer chip that was running this fast, the heat that it would generate was too much to handle, right? You had to have a heat sink. You guys who come up with these home-cooked computers that can play really good games or whatever, used to the idea that you have to have fans out the wazoo and heat sinks or whatever. And it's because the faster a chip runs, the more heat that it generates. And so the way that they get around that now is to improve performance. You don't just make it smaller and faster. You put multiple cores in it. So at one time you could only have one process running on a computer at the same time, but then you get your dual core processors. It can actually be working on 2 math problems at the same time rather than one. Or you buy your quad core and it can be working on 4 things at the same time. If we look up Moore's Law graph, Moore's Law is the observation that the number of transistors in an IC doubles about every 2 years. Okay, I said 1.5. They've changed it to 2. That's okay. They know better than I do. So it's a logarithmic scale. Trying to find a good example of that. I'm not going to spend much time on it. Anyways, if something is doubling every 2 years, you can get the idea that RAM sizes, well, let's write a little program that'll figure that out. Let's write a loop that will double every certain number of years. So file new project, Lecture H. And so since your Genesis and your Super Nintendo had 16 bits and were awesome, the PlayStation had to trump them all, 64-bit graphics, so that the graphics would be photo perfect. I think I created a C# app. Sorry about that. Let me make a C++ one. So what we're going to use is a loop, and it's going to take a number, and each iteration of the loop is going to double that number. So we're going to have a counter that goes like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we're going to have another value that doubles each time. So Solution Explorer, source files, add new file, new item. I'm going to go grab my boilerplate. Alright, let's ask the user how many years we want to track. So cout, track over how many years. And then let's create a variable called years, int years, and let's cin into years. And then we're going to have a countering value. I'm just going to call it X because I'm feeling really non-creative. How about C for counter? int c is equal to 0, and we're going to need another variable which doubles each time. So I'm going to call that one RAM. Maybe we're measuring megabytes, I don't know. But anyways, so int RAM is equal to 1, because you can't start doubling from 0, right? 0 double to 0, and then you double it again, and it's still 0. So we're going to start that one off at 1. Now we want a while loop. While c is less than the number of years, let's print out the value of RAM, or let's print out both. C out arrow arrow year equal end quote arrow arrow C arrow arrow quote \T for a tab, and then RAM equals end quote arrow arrow RAM arrow arrow ENDL. I'm going to put that on the next line. Then we need to add 1 to C, so C++, and we need to double RAM. So RAM times equals 2, or RAM equals RAM times 2, whichever one you like better. I might actually want to start RAM off like at 64, like we have a 64 bytes, or maybe it's 64,000, 65,000, because we have a Commodore 64 or something like that. But anyways, let's just let it run like this. All right, track over how many years. I want to see computing progress from just flipping a coin in 1 year. 10 years later, we have 512. All right, like I said, I want to take us from 64K up to something higher. So I'm going to change this 1 to 65536, because that's 64K, 64 kilobytes. And then I'm going to let it run. And the Commodore 64 came out like in, let's say, I'm going to just make up a year. Let's say that it was out in 1987, and so to go to 97 is 10 years, and go to 07 is 20 years, and to go to last year is 30 years. So let's track over 30 years. And kablooey, we blew out our variable. Our variable got too large. In other words, it exceeded the maximum capacity of an int, which is 2 billion. So apparently in year 15, we reached gigabytes of RAM. What type should I use rather than an int to hold our amount of RAM if we want to get it to larger than 2 billion?
Double.
Double is a good one. Let's use double. Or long. So I'm going to track over 30 years. Alrighty, if Moore's law was perfect, then in the intervening 30 years, oh, but it said every 2 years, we should be adding 2 to our year counter every time rather than 1. So if C is our year counter, I'm going to do C plus equals 2 to represent that 2 years went by. I really thought it was 1.5, but I'm not going to argue with Wikipedia. Okay. So over 30 years, alrighty, over 30 years, our computer went from 64K to whatever that is. 1 followed by that many zeros. That's only a billion. So there's something wrong with this calculation. It's not totally working right, but that's okay. But on the other hand, the 8-bit machines really were introduced in the 70s rather than the 80s, like the Apple II and stuff like that. So let's make it 40 years rather than 30. We may see slightly more realistic results. So over 40 years, alrighty. So we've gone from the gigabytes of RAM to 34 gigabytes of RAM. That's what it looks like. All right. That may be about right. What's the maximum RAM that people put in their laptops anymore? 16 gigabytes, something like that. So this roughly works. It's a rough approximation of RAM values from the 70s to now. Processor speeds work the same way. And if we were to graph this, it's not a straight line unless it's a logarithmic graph. If we put these numbers into Excel, we see it shoot like that. But like I said, you hit the physical limits where the traces of the wires and the transistors in them can't be made much smaller without great difficulty. You know, you talk about 16 nanometer, printing versus 8 nanometers, and they get so small that there's crosstalk. The electrons are skipping across the gap or whatever. So the processor speeds would have kind of leveled out. But then that's why they started doing the double core, the dual cores, and the quad cores, and the 8 cores, and stuff like that to try to continue to get them to go faster. All right, so that was a fairly significant diversion. Sorry about that. But you could apply the same idea to processor speeds. Let's just pretend. Well, let's find out how many clock cycles a good old Apple II did in hertz. That's not going to work. Okay, maybe if I type kilohertz or CPS or something. Okay, Apple II instructions per second. All right, speed of a 6502. This is going to be my last guess. Speed of, that's a processor chip that was in the original Nintendos and the Apple IIs and the original Atari computers. Clock speed of 33 megahertz. Yeah, 33 megahertz sounds fast, doesn't it? Well, our computers run in oh wait, but that's a vastly new and improved one. But now we measure our computers in gigahertz rather than megahertz, because mega means 1,000,000 instructions per second and giga means 1,000,000,000 instructions per second. Back in the old days, maybe the computers operated at 1 megahertz. You bought your computer in the 70s to play Lemonade games and things like that. So we're going to redo our calculator to start at 1,000,000. How about 1e to the 6? I think that means 1,000,000. But this is not RAM anymore. This is hertz. Instructions per second. I want to see if this chart looks anything right. Okay, so when did we hit gigahertz computing? Supposedly 20 years, after the 70s. So in the 90s, our computers finally started being measured in gigahertz rather than in megahertz. That could very well be. And this would imply something along the lines of 524 gigahertz. And I don't know if that's possible anymore, but at a certain point, like I said, it started leveling off. You could not just improve that much every 2 years or so. Okay, back to our lecture. We have powers of 2 involved. 0, 0, 0, 0, 0, 0, 0, 0. This is 2 to the power of 0. I'm going to put some 2's here. This is 2 to the power of 0 right here. Well, that's going to be hard to do. This is 2 to the power of 1. That's 2 to the power of 2. That's 2 to the power of 3. That's 2 to the power of 4. 2 to the power of 5. 2 to the power of 6. 2 to the power of 7. Right there. And so this is effectively the 1's place. This is effectively the 2's place. And 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power, right? You can see where this is going. 16, 32, 64, 128. Just keeps doubling each time. All right, something like that. That's not really well formatted, but you get the idea. When you're figuring out place values in a binary number, you just keep doubling them. That's for 8 bits. If you had 16-bit numbers, you keep doubling them still. 256, 512, 1024, and so on. So if I have this number, 10101, and I want to convert it from binary to decimal, here's what you do, right? Well, we're starting at 1, and so there is a 1 there. So 1 plus, and then do we have any 2's there? Well, there's a 0 there, so there's no 2's there, right? Do we have any 4's? There's a 1 there, yeah, so we have a 4. Do we have any 8's? No. Do we have any 16's? Okay, so though that number in binary is equal to 1 plus, looks like 21 to me. How about 01011? Do we have any 1's? We got a 1. Do we have any 2's? Do we have any 4's? Is everybody getting this? I hear 1 or 2 people answering. I hope you do. Do we have any 8's?
Yes.
Do we have any 16's?
No.
Okay, so 1 plus 2 is 3. Okay, so that's equal to an 11. All right, so what I want you to do is fire up Notepad or any of your favorite text editors. Just go to the start box, type Notepad, something like that. I'm going to give you all some binary numbers that I want you to convert to hex. And so just write your place values. To make it easy for you, I'm not going to give you anything more than 5. And your place values would be 16, 8, 4, 2, and 1. So tell me what 11111 is. Tell me what 01110 is. Tell me what 00011 is. And 01000. Yeah. Just do those 4. And I've given you several examples already. I'll keep those examples up here. A couple of people aren't getting it and some are, and that's okay. I'm going to go back down to 4-digit numbers just because I can represent them really easy, right? And so if I have this number, 1111, what that means is we have 1 8, so that's an 8, and we have 1 4, and we have 1 2, and we have 1 1. So if we added up our 8 plus our 4 plus our 2 plus our 1, we'd get our answer, which happens to be 15. Like I said, I care more about the writing down the process than the final answer. I don't care if we can do conceptually is what's important. Okay, so if we have 0101, do we have any 8's? And now I'm asking you, Angel. Check out this place. Where this is our placeholder right here. We're in the 8's column, but do we have any 8's? Nope. So that we're not going to say 8 plus anything. Do we have any 4's? Yeah, we do. So this is equal to 4 plus. Do we have any 2's? Nope. Do we have any 1's? Yeah, so that's 4 plus 1, which is equal to 5. Now, the ones I gave up here, they started with 16 rather than 8. So do we have any 16's here?
Yes.
Yep, so that's equal to 16. Do we have any 8's? And we have a 4, and we have a 2, and we have a 1, and you typed this into Google. What did it come out?
31.
31? Okay, yeah, all right. So does that make sense now?
Yes.
All right, cool. So if I ask you this on a quiz or an exam, I'm not going to ask you to do the conversion because you could just find the answer on Google incredibly fast, or you could pop up a calculator and it would do it. I'll show you how to cheat, and then don't cheat. Okay, so like 1020, or excuse me, 11110011 binary in decimal. It'll probably give us the answer. If not, you can find a binary to decimal converter, binary conversion. You can go out here and you can figure it out.
I didn't do that, I promise.
Yeah, I know. So if I ask you to do this on homework, I'm going to want you to type that out rather than just give me the answer. Okay, now going the other way is annoying. What do I mean by that? It's a process where you divide by 2 each time and you take the remainder. So what if I had the number 231? And I'm picking that arbitrarily because I don't know the answer, and that's base 10, but I want to convert it to binary. What you got to do is you got to keep dividing it by 2 and then taking note of the remainder. Because if you divide something by 2, but it has to be an integer, then you're left with either a remainder of 1 or not. So 231 divided by 2 is what? 115, am I right about that? And did we have a remainder? We had a remainder of 1. Okay, and then we have 115. What's that divided by 2? 57? And did we have a remainder that time? 115 was not even, so when we divided it by 2, did we get a remainder out of it or not?
Yeah, we got 1.
Okay, now we're getting down to the numbers that I can figure out a little bit more easily. What's 57 divided by 2? That's like 28, isn't it? Did we have a remainder there? No, no remainder. Yes, we did. 57 divided by 2 gave us 28 with a remainder of 1. Okay, but now we're in even numbers, so maybe things won't have remainders for a while. 28 divided by 2 is 14, and this is why I'm not going to ask you to do it. It's a little bit tedious. 28 divided by 2 is 14 with a remainder of 0, and then 14 divided by 2 is 7 with a remainder of 7 divided by 2 is 3 with a remainder of 1, and then 3 divided by 2 is 1 with a remainder of 1, and then 1 divided by 2 is 0 with a remainder of 1. And
7 divided by 2 is remainder like 1.
you're right. No, 14 had a remainder of 0, and then 14 divided by 2 gave us 7, and we still had a remainder of 0 at that point. But then when we took 7 down to 3, we had a remainder of 1. And when we took 3 to 1, we had a remainder of 1. And then so our answer is, and you actually copy from the bottom up in this case, so 231 is equal to, and I would count them from the bottom up, 1, 1, 1. Oh, what do you know? It's a palindrome. 0, 0. 1, 1, 1. I trust that that's true. I could figure it out. That's a 1 plus a 2 plus a 4. There's no 8s, there's no 16s, plus a 32 plus a 64 plus a 128. I'm going to trust that that adds up right. That's how you convert from decimal back to binary.
You're saying the most significant bit is
The bottom one, actually, correctly. If you do it in this fashion, you go up. Now, it just happened to be a palindrome. I chose a bad number. Yeah. Alrighty. That's probably about enough of that. I do want y'all to be able to do that conversion from binary to decimal. And then there's one more counting scheme that I want to mention. And then our brains may be broken enough that we want to end, but we'll see. We'll see. Okay, so besides binary and decimal and octal, which we're going to flush, there's one called hexadecimal. Hexadecimal is a counting system that has 16 digits, not just 10. So it's got more than 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, where do we come up with the extra digits? Are we going to just make them up? Well, they used the letters of the alphabet, A, B, C, D, E, and F. You know, and the Russians did not use A, B, C, D, and F because those weren't the 6 first letters of their alphabet, so their hexadecimal did not look similar to ours until, you know, everybody standardized their computers to all use the same thing. But anyways, so that means that our hexadecimal car counts quite a bit differently. We're cruising down the road. It takes longer. You know, we're going on. We hit 8, we hit 9. Do we roll over? Does the 1 increase yet? No, we haven't maxed out that column. We keep going. 0A, 0B, 0C, 0D, 0E, 0F. Now and only now have we maxed out our counting system. So the next time we add 1, this drops back down to the lowest possible value, and the next one bumps up by 1. And then it becomes 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, you know, and so on, all the way down. We keep going. Let's say that we finally get down to like 9F, right? We've counted that far. That's quite a ways. Okay, now we're going to add 1 to it. What happens? Well, the F changes to what? It's the max system, the max value in our counting system, so it drops back down to 0. And then we add 1 to 9. Well, if we're looking at our counting system, what's 1 greater than 9? 8. Okay, so now we're at A0. And we will go to A1, A2, A3, and so on. All the way up to, like, you know, say that we're at CF. Well, 1 greater than F is 0. And so C becomes a D. And if we kept doing that, eventually we get to FF, and the next one would overflow, would roll us over completely. So that's counting in hexadecimal. Quite a bit different. So you'll wind up seeing numbers like 001B, 1D, 8OF. I'm just making this up purely off the top of my head. But anything that has a numeric digit of 0 to up to 9, and then the letters A through F is fair game for hexadecimal. If we wanted to convert a hexadecimal number to base 10, we need to know the powers again. But they're not powers of 2, they're not powers of 10, they're not powers of 8, they're powers of 16. So if we have 4 places in hexadecimal, like FFFF, the maximum value that can be held in 4 digits of hexadecimal, this one is 16 to the power of 0. This one is 16 to the power of 8. Excuse me, 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, and then 16 to the power of 3. And my brain doesn't work like that. I'd rather see the real numbers. Anything to the power of 0 is 1. 16 to the power of 1 is 16. 16 to the power of 2 is 16 squared, which is 256. And then 256 times 16, I believe, is 4096. I could be wrong. I better check that. Okay. So, those are our place values. Right there. So if I gave you this number, 1076, and I wanted you to, in base 16, which you can represent like that, or you can call it OX 1076. This is a very common nomenclature. It stands for hexadecimal 1076. What is that in base 10? We would just have to add them up. How many 4096s do we have? Well, let's write this 1076 out in a format that's easy to understand. 1076. How many 4096s do we have in 1076? We have 1, right? So we have a 4096 plus, how many 256s do we have?
0.
And let's just skip that one. How many 16s do we have?
7.
Yeah, whatever 7 times 16 is. And then how many 1s do we have? 6, okay. And then I can just copy that and paste that into Google because I'm not going to do that in my head. All right, so that's equal to 4214. It gets a little bit crazier if we use our letters as well. What if we had 10AB? Well, then we have to remember what A and B actually mean. let's count them down like this. 0, 0, 0, excuse me, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. That's the hex column. And then the base 10 column, that's equal to a 1, 2, that's equal to a 3, that's, I goofed there. That's a 0, that's a 1, that's a 2, that's a 3. And it's going to be a 1-for-1 match until we get past 9. Okay, well, what's 1 more than 9 in decimal? 10, so that's a 10, that's an 11, that's a 12, that's a 13, that's a 14. That makes that a 15. Just, that's your digits of equivalency. So now I'm going to copy and paste this down closer to my conversions where I was doing this stuff. So if we have 10AB and we want to convert that to decimal, well, how many 4096s do we have? We've got 1. So 4096 plus how many 16s?
0.
So we skip that. How many? I think I goofed. That was 256s. I should have had this hanging around to make it easy to count. Right. Okay. So anyways, this part was right. We have 1 4096. We have no 256s. And we have A 16s. Okay, well what was A? A is 10. So we have 10 times 16 plus, and how many 1s did we have?
11.
Yeah, right. We have B number of 1s, which is 11. Okay, cool. What if we have A? All A's in base 16. What does that equal to in decimal? Well, we can figure that out pretty easy. What did we say an A was? 10. So we have 10 496s. How many 256s do we have? Yeah. 10 times 256 plus 10 times 16 plus, and how many 1s do we have? 1 more 10. Okay, so I could take that then and copy it into Google, and they would tell me the answer. Like I said, I don't care about the math as much as I care about the fact that you can write down those additions. All right, so I'm going to make one up for y'all to do. So pop your notepad back open. I'm going to try not to make it too traumatic, and I don't even care if you add them up actually. I just want to see this part. So here's our placeholders, and here's the number that I want you to do. Like that, 11AF. Convert that to decimal. And remember that an A is equal to a 10 and an F is equal to a 15 when you're writing this out. And I'll get you started. 1 times 4096 because we have a 1 in that column. right, so you missed that one. I'm pretty sure you got it, but we're going to add this one up anyways. So how many 496s do we have? We've got one. 496s. How many 256s do we have? One. Plus how many 16s do we have? 10. And how many ones do we have? 15. So 15 times 1. And then me being lazy, I copy all that. I go to Google. I paste it. I get my answer. And I get 4527. And I don't care about that nearly as much as I care about the fact that you can write these additions down. Okay, so we're going to take a little veering off to the side and go back to binary. Do you remember up here, I started counting in binary using 4 digits, and I got, let's see if I can find it. Oh, I think I have 2 notepads going. Okay. There they go. Right, I counted out 0, 0, 0 all the way to 1, 1, 1, 1, and I got 0 to 15. Well, what do these look like? Didn't we just look at these 0 to 15? Doesn't that seem awfully familiar? That's a 0, that's a 1, that's a 2, that's a 3. Where are my letters going to start? Which number am I? At 10, right. So that's going to be the first one that's unusual. All right, so I can just flesh these out. If I ever ask you on an exam to do some conversions, I'm going to give you this chart because I don't want you to spend time having to write this out by hand. But what is that chart good for? Besides boring you and making you wish you were going home. We can use it to do direct conversion from binary to hexadecimal or back. Because I wouldn't want to take hexadecimal to decimal and then start doing that divide 2 business. Or I wouldn't want to convert the binary to decimal and then somehow convert it back to hex. That would be a real pain. But I could use this chart. Let me show you what I mean. Say I have that hexadecimal number of A01F. And I want to convert that to binary. This is just a simple lookup. Well, what's an A? It's 1010. Well, what's a 0? It's 000. What's a 1? 0001. And what's a F? All ones. That makes sense? Simple lookup. Let's come up with another one. Let's say that we have, for some reason, I just type those in, but OXDEAF. Let's convert those. What's a D?
1101.
Right, 1101. And by the way, you don't have to put the spaces there, but it makes it a heck of a lot easier to read. What's next? What's an E? 1110. What's an E? Wait, I goofed that one.
No, just the next one.
Yeah, the next one's an A. So an A is 1010, and an F is all ones. All right, I'm just going to totally make one up, and I want in your notepad you to do it. And by the way, this is why hexadecimal was even invented, because of the one-to-one correlation between 4-bit values and hexadecimal values. Because if you had to look at a page of zeros and ones, your eyes would cross, like you were looking at one of those magical pictures where you're supposed to cross your eyes and suddenly it becomes three-dimensional. You know, it would blow your mind to look at an entire page of zeros and ones. The best thing to do would be to convert it into some form where clusters of bits, either 3 bits or 4 bits, would be represented by numbers. First, somebody chose 3 bits, and so they invented octal. And then, you're going to use 4 bits, because everything loves to be in powers of 2. And so you could represent, you know, a dump of memory, which was all zeros and ones, in hexadecimal form, and it would make more sense. All right, so what is my 7 here? Somebody typed it in their notepad, so tell me.
0, 1, 1.
Okay, what's next? What's that 5?
0, 1, 0, 1.
And what's a B?
1, 0, 1, 1.
And a C is one more than that. What is it?
1, 1, 0, 0.
Right, okay, so there we go. And converting back is just as easy. Right, so I'm going to make up a series of 4. By the way, little clusters of 4 are called nibbles, absurdly enough. 8 clusters of 8 are called bytes. So these are actually 2-byte values, because there's 8 plus 8 more, that's 2 bytes long. So when we were talking about 32-bit values and 64-bit longs and stuff like that, and so a 64-bit long was actually 4 bits, 4 bytes wide. Well, it would be 8 bits plus 8 more, plus 8 more, plus 8 more. That would be 32. And then if you're going to go 64, you'd do 4 more groups of 8 like that. So, 1011, 0010, 0100, 1110. All right, and then if I'm going to convert that to hex, I would just look them up in reverse. What is a 1011? A 1011 is a B. So I'm going to put 0x there to represent that it's in hex, B. And then what is an 0010?
2
That's a 2. What's an 0100?
to 4.
And lastly, what are all those ones and zeros?
14.
Yep, that's a 14, which is an E. Okay, so we took binary and we converted it to hex. So I'm just going to make up one more, and then if y'all would type this in a notepad. Convert that series of hex into binary. Excuse me, that series of binary into hex. All right, race to the finish. Who's already got it? Tell me what the first one is.
F.
That's an F, and what's the next? How about the next? That's a 9, and lastly, 6? Yeah, looks like a 6 to me. Precede it with OX to represent. Okay. So, a little more comments I want to make. As I mentioned, 4 bits equals a nibble. That's silly. It's half a byte. 8 bits is a byte. In C, or in the modern C standard, an int is equal to 4 bytes is equal to 32 bits. A long is 8 bytes, which is equal to 64 bits. One thing that I haven't mentioned when we were doing these conversions is that you can have either signed or unsigned numbers. So far, everything we've been doing is unsigned. There's no way to represent a negative number in the counting system that we've been using so far. Like if we wanted to store negative 14 in binary, we'd have a problem right? We've only been doing positive ones. You know, we could look up, you know, a 14 and we could say, oh, it's supposed to be 1110. So what they've decided is that unsigned values follow these rules, but signed values would begin with a 1 at the beginning of the byte, or at the beginning of the 2 bytes or 4 bytes or 8 bytes, or, you know, whatever the data size is. So if you were going to represent 14, you could say that that was 1110, and then we could pad it out to like 4 bytes to making it an int, but that's just a nibble I need to add, you know. Let's just pad it out to 1 byte. Okay, so that would be 14 in 1 byte. Negative 14 in 1 byte. This is a simplification and it's not correct, but it's close. The first bit is used as a sign bit. So if you saw 1 followed by some values, you would take this value and then you would say it was negative. Now that's not exactly true, because what they do is they use something called 2's complement. And the reason they do that is because if the first bit is a sign bit, then what would this mean? Well, if you ignore the first one, then what's that equal to? 0. Okay, and then you stick a sign bit in front of it to make it negative. What does that mean? It's negative 0. That's ridiculous. So they switch it up a little bit with something called 2's complement that I'm not going to explain. But what I want you to know is that if you have 1 byte and it's signed, you only have 7 bits of data to play with. And then the last bit determines whether it's positive or negative. So if you have an int, which is 4 bytes, you know, you have 1, 2, 3, 4, 5, 6, 7. You have 31 bits to contain your data and 1 bit to determine whether it's positive or negative. And do you remember that little equation I said that would tell you what the largest possible value is? It was 2 to the power of 31. If we go and we type in 2 to the power of 31, 2 to the power of 31, what we'll see is that number that we've seen a lot. That the largest value that an int, that a signed int can hold is about 2 billion. And the smallest value it could hold would be about negative 2 billion. But if it's unsigned, then you get to reclaim that bit. And so then, you know, instead of being limited to about 2 billion, you get 2 to the power of 32, which is about 4 billion. But you can't go negative. That's why you might want to use unsigned numbers if you need to hold numbers that are slightly larger, right? But you never need to worry about them going negative, then you can make them unsigned. But that's why 1 int can hold about 2 billion. And if we were going to do a long, then we would have 2 to the power of 63. Sorry to switch up the caret for the stars. This is how you do it in Python. And so anyways, 2 to the power of 63 is, why not 2 to the 64? Because this is signed, so we lose the first bit as our signed bit. So 2 to the power of 63. Big number. It can hold far larger numbers, 9 followed by 18 zeros. Whatever that is, right? Millions, billions, trillions, I don't know. So, longs can hold much larger values. So they're good. However, doubles can hold far larger still because they can hold exponents, so they can hold vastly more. But floating point numbers are stored in a different scheme. This is not it exactly, but if you had to make a floating point system out of 4 bytes, could do is you could say, I'm going to use the first 2 bytes for my value, and then my second 2 bytes for the exponent, right? And so that would give you the ability of having, you know, a number of 65535 up to, you know, times 10 to the 65535, something like that. That would be your largest value, right? And I never can remember what the first part of an exponent is called. It always flutters into my mind and then back out. This is the exponent, and this is the, my brain jumped to meniscus, which is the curvature of fluid in a test tube, and that's not right. Pardon me?
It's not mantissa.
Mantissa is the term, or it's very close to it. I've read 2 terms for it, and that's one of them. So you could use the first 2 bytes for the mantissa and the second 2 bytes for the exponent. But maybe you don't care to make your number so huge, and you want more digits of precision, right? You could make the first 3 bytes the mantissa, and then the last byte, you know, the floating point, the exponent. But I don't think that's exactly what they did either. We could go up and find the IEEE specification for floating point numbers and find out how many bits the mantissa is and stuff like that. And that is enough. I think I've talked enough about this. So why don't we make a Dropbox just so that you can upload that notepad thing. And if you're watching this at home, and I would like for you to try to do the problems that we did, but I know that we gave you the answers. I should create a worksheet for this. That'll be a homework assignment. I didn't create that one yet. I have one that I've done for other classes, but I'm not going to make 2 and Vincent just repeat the same one.